Okay. Today we'll start with this basic introduction to this VLSI. I think my screen is visible. Okay. See here. Basically, like VLSI, so evolution of logic complexity in integrated circuits for information technology and services. So these are the outlines like evolution in logic complexity in integrated circuits, evolution of size in integrated services, prominent information technology services, and features of integrated circuits. Okay, this will see. So basically, evolution of IC, if you see, so like there is evolution of IC. First is what medium scale integration. So medium scale integration means they introduced during the year 1967, and logic block per chip. How many logic block per chip are there? There are 20 to 200 logic block chip are available. Okay, and LSI, that is large scale integration. So they introduced around 1972, and logic block per chip is 200 to 2000 per chip are available. Okay, and next is very large scale integration. They introduced around 1978. Logic block per chip is around 2000 to 20,000. Logic block means it consists of some combinational and sequential circuits also, that we call as logic block. Ultra large scale integration, so this is introduced during 1989, and logic block per chip is 20,000. Okay, so this is the evolution in logic complexity in ICs. Okay, uh, so basically like size in integrated circuits, like Moore's law given a statement that every year, every 18 months, the transistor count doubles. Okay, that is nothing but Moore's law. This is in terms of microamps, and this microamps. So basically, like 1975, we are at which means 4 micrometer technology, and when you come to 2000, we came up to zero point 0.1 micrometer technology. Now 2025, we are in which technology means we are working under nanometer technology, 3 nanometer and 2 nanometer technology. So this technology is nothing but what? Gate length. This technology is nothing but what? Gate length. We already seen the MOSFET, no? So MOSFET, that is gate length, that is nothing but the technology. Okay. Is it fine? Give response so that I will move forward.
Yes, sir. Okay.
Okay.
Yes, sir.
Yes. Next you say prominent information technology in this. So basically 1975 to 1985, mainframe computers came into picture. Okay, and 1985 to 1990, we used personal computers, and 1995 to 2000, we used computer networks. This is related to computer technology. Okay, and above this, there are consumer electronics also there. Consumer 1980 to 85 means like televisions came, some washing machines. Consumer electronics means whatever the electronics we are using for household applications, that is nothing but consumer electronics. Okay, and portable. So 1990 to 2000, portable computers came. So portable computers are nothing but what? Laptops means what? Portable means what? We can carry. Okay, so those are battery operated, and nowadays we are using laptop, no? So laptops are nothing but portable computers. So they came into into market around 1990. So till now we are using this portable computers. Okay, and coming to the communication, in 1980 to 1990, data communication came. Okay, data communication came, and 1990 to 2000, multimedia applications came. Okay, and next you have like wireless or cellular communication. So communication, we got the mobile phone, no? Previously we have like landline phones, but when mobile phones came into picture, so mobile phones use which communication? Wireless communication. The medium is what? Wireless communication. And cellular data communication. Okay, cellular data communication came into picture during 1985. And this is speech processing. Okay, speech processing. And video on demand, like video on demand means 1990, multimedia and graphics. Graphics came into picture. Now we are working with, we are in VFX. Okay, so most of the movies, we are they are shooting in VFX. Okay, like VFX technology. Okay, so these are the prominent information technology services. Okay, so features of integrated circuits, if you see, so it should take less power and less volume and less power consumption and less testing requirements at say system level. Okay, less testing requirements at system level, high reliability. Okay, mainly due to improved on chip interconnect, and it should be high speed. Okay, and cost saving, significant cost saving also required. These are the features of any IC, integrated circuit. Okay, uh, so if you see the methodology, this is VLSI design methodology, design time, performance, and technology window. We'll see. Okay, so design time. So if you see, like there are like full custom design. So performance analysis, if you see, there are two types are there: full custom design and semi custom design. Okay, so full custom design means what? Full custom design means so here it will take suppose if you see the full custom design, it will take longer time design until maturity. Okay, it will start from the initial state and it will take longer period, mostly it will take 1 year of time. Okay, 1 year of time. And here so when this design is completed, more opportunities for the performance to be improved. Okay, so I will tell you one example. Whereas semi custom, it start from here. Okay, semi custom, what they will do, they will take some standard cells are nothing but, suppose in the digital we already seen some adders. Okay, gates and flip-flops. Okay, counters. Okay, so those are pre-designed, and they will take and they will use that. Okay, here full custom design means they will make their ICs from the scratch. Okay, semi custom means they will take some standard cells and they will implement in their design. Okay, so that means this will take shorter design time, so it will take around 6 months only. Okay, it will shorter design time. And so here quality is more. Full custom design quality is more, but here semi custom design less opportunities for the performance improvement. One means it can work up to 5 years. After that some problems will arise. Okay, so okay, so like full custom and semi custom design, I will tell you with one example. Suppose if you take mobile phones. Okay, mobile phones, you have like full custom design, full custom you have iPhone and Samsung. Okay, these are nothing but full custom design. Okay, so if you see in the market like every 1 year one model will be released. Okay, and the cost is also very much high. So that means like iPhone 7, iPhone 17 now, I think it's around 1.5 lakhs, 1 lakhs to, it ranges 2 lakhs. Okay, so it will be cost is more. So that means quality is also good. Quality is also good. So they have their own ICs and they will come up with the design of full custom design. Okay, so that means performance improvement will be there. More opportunities are performance improvements. Okay, Samsung also this is a product based company. They have their own manufacturing units. They will make their own ICs, so that, so what they will do, they start from the scratch, like ASIC means application specific integrated circuits. So they manufacture these ASICs and they will be long run. Okay, Samsung phone also with all um, mm, properties in the mobile. Okay, all the features in the mobile, it will be 80 equal to 1 lakh. Okay, so 1.5 lakh also available. Okay, so that means cost is more, but quality wise it is good. Okay, semi custom design, if you semi custom design, suppose if you take like mi, okay, oppo and vivo. Okay, some phones are there, no, oppo, vivo, these phones, okay, realme Realme phones. Okay, these will follow what semi-custom design. Semi-custom design. Semi-custom design means suppose MI phone is there. So MI phone. So which processor it will use? Qualcomm Snapdragon. So that means it will purchase the processor. It will take the processor from the Qualcomm and it will assemble. Okay, so that means for DSP processors, also for display also they will purchase from different whoever are specialized in that design. They will take these standard cells. Okay, whatever the standard cells are, they will assemble. Okay, so quality wise, after 5 years you will get some problem in the battery or some problem in the display, like that. And quality wise, this is less opportunities for the performance improvement. And next year, within 6 months, if you see in the market, 2 to 3 models are released. So time to market, okay, shorter design time is there on maturity. Okay, shorter design here, this is longer. It will take 1 year and it will take 6 months of time. Okay, 6 months of time. And so this will follow semi-custom design. And cost is also, so this is one third less than the full custom. That means if you purchase for like 30,000 rupees, so whatever the features present in iPhone or Samsung, that features will be available in these phones. Okay, so this is about the performance analysis versus design time. Okay, so basically those are two types: full custom and semi custom design. Okay, do you understood? Any doubt in this?
No, sir.
Okay.
No, sir.
Yeah, next you see. So technology window. So how the technology window will be there? So first design. Okay, circuit performance, design, production, and technology window, design, production. Like this it will be there. Okay, technology window. Okay, and next I told you, no, full custom design and semi custom design. So this is the difference between full custom and semi custom design. Okay, full custom design means what? So complete design layout, geometry, orientation, and placement of transistor is done by the designer. Okay, they will come from the scratch. Okay, that is nothing but full custom design. So here in semi custom design, what they will do, some commonly used design and layout or geometry and placement of transistor is interfaced with the given device. So already some designs are there. Suppose if you consider flip flops, gates, okay, or some counters, okay, some already predefined ALUs, already they are designed. Suppose our company, one company, TSMC. Okay, TSMC, this company will provide these semi-custom products. Okay, semi-custom products, they will take from that, and they will interface for the given demand. So what is the demand is there, so they will interface. Okay, um, here entire design is made without the use of any library. Okay, without use of any library, entire design will be there. Here design is completed with the use of multiple libraries. Okay, standard cells are there means what, you have standard libraries. Okay, so standard cells they are using standard cells means they have some standard libraries. With the help of the standard libraries only, they are fabricating, means they are using some design rules and design geometry. Okay, layouts. Okay, based on the library only they are using this. Okay, this is a semi custom design. Okay, so development time for the design before maturity is more. Okay, before maturity is more. I told you, full custom design will take 1 year of time. When it will come and so when it come to maturity, it will take 1 year of time. Okay, development time for the design before maturity is less. Okay, it will take 6 months of time. 6 months of time. Okay, it has more opportunity for performance improvement. So quality wise, this is good. Quality wise, this is good quality, full custom. Okay, less opportunities for the performance improvement. So quality wise, we can't access. That means we can use I told you mobile phones, no, we can use for up to 5 years. Okay, after 5 years, what happens? Problem comes like draining of battery fastly. Okay, just my example only. I am using mi this 11T Pro, 11T Pro, Xiaomi 11T Pro. 11T Pro I am using for last I think 5 years, I think so. There is a problem with my battery like it's draining fast. Okay, so that problem arises in my phone. Okay, so in my phone, so why so that time I don't have idea like what mobile I need to purchase. So that means I purchased a semi custom design mobile. Now after 5 years, 3 to 5 years, I got the problem. Now I know what is full custom design and semi custom design. So next time if I want to purchase any mobile, so I will go with full custom design only. I can purchase Samsung mobile or I can purchase iPhone. Okay, so why? Because I know the problems in semi custom design, how they are preparing. Okay, so as a VLSI engineer, you need to know, have the idea about what is this full custom and semi custom design. Okay, so here this less depends on the technology wise this is less dependent. Okay, this is completely depends on existing technology. Whatever the existing technology is there, this is completely depending. Okay, this is high cost, I told you, no. So with example I told iPhone or Samsung. Okay, Samsung, so these will be in terms of lakhs only. Okay, so this will be in terms of above 50,000 you take 50,000, above 50,000 the price is there. This is low cost. Okay, like mi Vivo, Oppo. Okay, these all are China phones. Okay, Oppo and Realme. So this cost is less than one third cost. Less than one third cost of this full custom design. That means within this 30,000, you can get all the features of that means whatever the features you have, that all the features you will get. Okay, so that is full custom and semi custom. Now you understood about this full custom and semi custom design. Shall I move forward?
Yes.
Okay. Next you see. So this we already discussed. One second. Yeah. Semi-custom design. Semi-custom design is nothing but what? Why we are using semi-custom design? This is method is used to reduce the time to market. So much competition is there. No, so much competition is there. We need to design. We need to reduce the. We need to reduce the design time. Okay, how to reduce the design time? We need no need to waste the time for developing from the scratch and like that. So already whatever the predefined standard cells or predefined technology is there, they are using in the semi custom. Okay, so by using this here means if we start from the scratch, so we need to invest more for design engineers. Okay, layout engineers and physical design engineers, front end design engineers. Okay, so means already predefined designs are available, they will take. Okay, so we can reduce the cost of designing of the product. Okay, cost of designing of the product, equipment product and all those things we can reduce. Okay, performance wise, if you see semi custom design is lower than the full custom design. I told you, no. So the quality is very low compared to full custom design. Okay, so so in semi custom design what happens, already readily available blocks are available. So I told you, no, like suppose already standard cells are available. Okay, gates are there. Okay, gates and adders. Okay, comparators. Okay, decoders. Okay, and flip flops, counters, shift registers. Okay, and sequence generator, some already predefined design is available. So they will take this, they use the readily available blocks, design and library modules. Okay, already they will use these designs. Okay, and so if you see the classification of semi custom design, they are classified into three types: standard cell, gate array and programmable logic devices. Okay, standard cell, gate array and programmable gate array. Okay, standard cell is nothing but I told you, no. So here uh, we use standard library in the standard cell. So basically like few hundred cells including we are using inverter and gates NOR gates, complex AOI and OI gates. Okay, AOI is nothing but what? And or invert, and or invert. We already seen now when you are implementing with the NAND gate and NOR
Yes.
gate, that we need to develop with what, and or invert, no?
And but
Yes. OAI is nothing but what? Or and invert. Or and invert. Okay?
inverter.
Inverter. Or and inverter. And D latch, flip flops, and counters. Okay? Those are readily available in the standard set. Okay? Those are readily available in the standard set. Okay? So these gates with a different driving capability, for example, standard size, okay, double size, quadruple size, okay, we'll make based on this some like when we take that standard cells, there is a like some manual will come, okay. So based on that manual they will give how much of size, how much of drawing capability, how much power it will take, what is the clock frequency, like that whole thing will be there in the manual. Okay, based on that manual only we will we call as a data sheet. That is nothing but data sheet. Okay, within the data sheet, by seeing this data sheet we need to design that circuit. Okay, uh, we need to use size based or current driven capabilities. Okay, design sends a schematic fabric. So here my requirement is there, I want suppose D flip flop, I want to design D flip flop. Okay, so when I want to design D flip flop, so here designer, whoever the designer is there, designer send the schematic to the fabricator. Okay, who fabricator, what they will do, they will prepare the mask if the cells are from the library. Okay, so like I told you one company, no, TSMC company, they have a predefined standard cells are available. Okay, already support designer want some AND gate, okay, NAND gate. Okay, he will send this design schematic to the TSMC. Based on his requirement, they will make this. Okay, so they will make, if already available means they will just they will provide this product. Okay, like that. Okay, larger library and larger cost and standard cell guarantee that it will work. Okay, so here what are the advantages? Flexible design, work with analog as well as digital functions, sophisticated system can build easily. Okay, and mask cost is more. Okay, that is one of the disadvantage. So this is about the standard cell. Next, gate array is nothing but this is prefabricated circuit with no particular function. Okay, like suppose FPGA is there, field programmable gate array. Okay, FPGA, what we can make FPGA are nothing but what? Configurable. It consists of what? CLBs. Okay, so here there is no prefabricated circuit with no particular function. So this will be like what we call universal. We can call as universal circuit. Okay, suppose if you want to design some adder circuit. Okay, if you want to design some adder circuit. Okay, so what you will do, you will write the Verilog code. Okay, you will generate the netlist. Okay, that netlist, from that netlist you generate the bit file. That bit file you will port that into FPGA, so that FPGA will work as this adder circuit. Okay, so only mask for metallization is needed to be created. So this will reduce the mask cost, less time. Okay, decided size is fixed. Okay, we can't reduce the size. Okay, number of transistors also fixed, metal height is fixed, two metal layer is possible, low efficiency, suitable for low production. So this is not suitable for large production, we use only for R&D purpose. Suppose if you want to check the circuit functionality, then I can use for gate array for R&D circuit. Okay, this is field programmable gate array. Programmable logic devices are nothing but so basically this FPGA consists of SRAM. We already came across RAMs, no? Okay, SRAM means what? When power is down, whatever the content, whatever the programming part will be there, that will be that will be erased. Okay, that will be erased. So where you are using this FPGAs means, suppose you are using in cell towers, okay. So in cell towers, what happens, suppose we are previously which technology we used, 3G technology, no? Previously we which technology used in the phones, we used 3G. After that 4G came, next 5G. Okay, after 2 to 3 years, what technology will come, 6G will come. Okay, so 6G will come means, here every time suppose towers are there, every time suppose tower is using only for 3G technology, every time you can't reinstall the tower, no? Every time you can't reinstall the tower. So what happens, so here there is a program you already written in 3G. Okay, you are using FPGAs. Okay, so FPGA is working under this 3G, always below the tower. Okay, this is a tower. So below the tower, what happens, there will be a generator, what happens, why? Because FPGA is using, FPGA means when power is cut down, whatever the data is there, that will be gone. Okay, so this generator, when power is shut down, so generator immediately it will give the power to this cell tower. Okay, so here now we upgraded to 5G. Okay, so when we upgrade to 5G, so just no need to reinstall the whole tower, just we need to change the program, and that we are loading, and the tower is acting as a so that tower can support 5G, the tower can support 5G. Okay, so like this is field programmable gate array. Next, what is ASIC? ASIC is nothing but what? Application specific integrated circuits. Application specific integrated circuits. Okay, application specific integrated circuit means those are only for the particular application. Okay, suppose your mobile phones are there. Okay, mobile phones are there. Suppose one person is using 3G mobile. Okay, so 3G mobile means now 5G came. Okay, now 5G came, so it will not support, it will not support 5G. Okay, so what they will do, what the this providers, what they will do, so most of the people, they are using 5G, so whatever the band is there, they will allocate this frequency to 5G only. So what happens, this network will drop. Okay, he will go to shop and he will ask that this network is not working, like that means, simply we will tell most of the providers are 5G, so we slow down this 3G. So one option is he is using only ASIC. Suppose he want to go for, he want a good network means, he need to upgrade to what, 5G phone. You need to purchase 5G mobile. Okay, and this size also, suppose if you are using 128 gigabyte, okay, 128 gigabyte and 8 GB of RAM. Okay, 8 GB of RAM. Suppose you want you got some requirement, you want 256 gigabyte or 512 gigabyte in the internal memory, 16 gigabytes, that phone you can't upgrade. Okay, so that is nothing but only used for a specific application. Okay, your wristwatches, your health monitoring watches are there, that is only used for specific application. Your ACs are there, washing machines are there. Olden ACs, they are we are using with the remote. Okay, now TVs, ACs, they got like advanced technology. They are using AI in this AC, artificial intelligence. Okay, so artificial intelligence means you can, like IoT, you can monitor your AC outside your house also through this IoT technology. So can you upgrade with this old AC? You can't upgrade, no? So these are nothing but ASICs. Okay, ASICs means we can use for bulk production, and this will take low power, and whatever you are using the application, those are nothing but ASICs only. In automobiles also we are using that ICs for airlock, means that when accident occurs, no, so that that airbags will open, okay, and auto lock braking system, engine control, okay, like so many ICs. In medical also we are using so many ASICs. Okay, so like when this is only used for specific application, that is nothing but ASIC. Okay, this is FPGA is nothing but this is used for only for the general purpose. We can use for R&D purpose, general purpose you can use. Okay, once a program is written, we can't change. Those are nothing but ASICs. Okay, so hope you understood the difference between ASIC and FPGA. Okay, and so programmable logic devices means you have simple programmable logic device, complex programmable logic device, and FPGA. So what is the difference means here, in CPLDs PROM will be there. PROM will be there means when you are programming, this will be permanently stored. Okay, permanently stored, this will be not erased. Okay, and in FPGA what you are using, if in FPGA you are using SRAM technology. Okay, SRAM means what, this is volatile, no, so volatile means what, whenever the power is gone, all the programs will be erased. Okay, so this is FPGA. And hierarchy, if you see, so this involves dividing the complex design into various modules. Okay, so like transistor level, first if you see micro block level, suppose if you want to design CPU, this is micro block. Okay, macro block, and CPU is made with what, micro block means what, ALUs, combinational circuits, and sequential circuits. Okay, these all are nothing but ALU, and identical gates like universal gates, NAND gate, NOR gate. Okay, and these gates are made with transistors, CMOS. Okay, this is nothing but it should follow the regularity. Okay, so mostly there is a top down approach and bottom up approach. Okay, top down approach means like we'll use the block level, SoC level, okay, and here transistor level. Okay, and bottom up approach means transistor level and SoC level. Okay, so basically in VLSI we use the top down approach only, not bottom up approach, top down approach. Okay, we will divide our larger complex circuits into smaller. SoC is made with some modules are made with some modules are made with some gates. Okay, or combination or sequential circuits. Okay, and these are made with gates are made with transistors, like that. Okay, this is like regularity, modularity, okay, locality. These are nothing but basic things, okay, that you need to know. Packaging technology. So packaging technology, like there are a whole package, surface mount package, contactless package. Whole package means in the BTech you already seen SIP, dual inline package, PGA package. Okay, basically you will use dual inline package. SIP means what, single line package, only single line you have that IC leads. Dual line means what, dual inline package means you already seen the IC, no, this is IC. Dual inline package means here the leads will be there, and in the lab we already seen, no, like in the some electronics lab or ECA lab. Okay, so you already seen this dual. And pin grid means what, pin grid means some like so this grid type pin grid type material is there. Okay, that is pin grid type. Okay, single line package having single row of lead SIP. Okay, less number of leads in single row. Okay, so dual inline package means there are two rows are there, I told you, no. DIP are mostly used in educational institutions. Okay, and PGA means what, package grid arrays. PGA having grid arrangement. Okay, grid arrangement basically like grid arrangement means, have you seen the processor? This is a processor, four sides you have leads, no, this is grid arrangement. Processor IC, have you seen that processor IC, 4 sides you have leads, maximum 400 pins you have in grid array. Okay, so this is grid array. And there are surface mount package. Okay, surface mount means like holes, we are in the in the PCB, on the surface of PCB we are mounting this ICs. Okay, contactless package, without contact also we can make this ICs. Okay, uh, design flow, basic design flow. Basically you need to understand about Y chart. Okay, this is the design flow, design specification, architectural design. Okay, gate level design. Okay, basically you know the design flow. Give response so that I will explain. Hello.
No,
Explain,
sir.
sir.
Okay, yeah, you don't know. Okay, I will explain you. Design flow means suppose one second, this is not clear one. I will show you clearly. One second, I will open this. Mm, not this one. Yeah, this one. This is the total ASIC. I told you, no, ASIC means what? Application specific integrated circuit. Okay, so this is flow. First design specification. Design specification is nothing but, suppose client is there. He will come with some inputs. Suppose if you want, he want half adder. I'll tell you with simple application. Half adder how many inputs? Two inputs and two outputs, no, sum and carry. So what is the behavior of half adder? It will add one bit and it will produce the sum and carry. Okay, it will produce the sum and carry. Okay, so these design specification, what are the specification, how much power it will take, and what is the clock frequency. Okay, those all specification will be given by the client. Okay, this is nothing but design specification. Okay, and next architecture means what? So they will do the planning. They'll do the planning. Architecture means what? They will do the planning, means so suppose they want to design some CPU. Okay, CPU means what? CPU means this is a CPU. So in the CPU what will be there, you have ALU. Okay, and here you have memory, and here you have control unit, and here you have memory unit. Like this they will do the total planning or architecture of the design. Okay, after that micro architecture. So micro architecture means in the CPU what will be there? ALU is there, memory unit is there, control unit is there, and control unit is there. So okay, and this bus interface unit is there. So all these are nothing but what? Micro architecture. So they will do the micro architecture. So they will design each and every architecture separately. Okay, and RTL design is nothing but register transfer level. Register transfer level. So register transfer level, this will discuss. Okay, register transfer level means basically you have HDL, hardware descriptive language. Okay, so basically there are two types are there, Verilog and VHDL. Okay, so this VHDL is came into picture in 1999. Verilog around 2001 you got, but basically this VHDL used in defense purpose. This Verilog we are using in the, wherever you go you are using this Verilog only. Okay, this is universal. Okay, and this will follow C syntax. This will follow ADA and olden languages are there, ADA and Pascal. These languages it will follow. Okay, so this is universal. So we can we can easy syntax are there. Okay, and easy to learn. This Verilog easy to learn. Okay, so this is design language. So RTL means in the Verilog 4 level of abstractions are there, switch level. Okay, and next gate level, and data flow level, okay, data flow level, and next behavioral level, okay, behavioral level. So basically we'll use these two levels in the RTL, okay, this RTL, okay. So basically the data flow level and behavioral level we'll use in the RTL, that I will explain you, don't worry, that we'll discuss. So register transfer level means it shows how the data is transferring in the register is nothing but register transfer level, okay. Next RTL, so RTL designers will design, okay, they will design this modules, okay, micro architecture or like ALU, MU, or they will design the small units also, but the foundation is digital only. This ALU foundation is digital only. This ALU is they will design by using what combinational circuits, okay, and memory unit they will use sequential circuits, okay. So if you are strong in the digital, then you can write the Verilog code. You are describing your digital circuits in form of textual form, okay, textual form, that is nothing but RTL, okay. So that we can verify the circuit also. Suppose if I write the program for the half adder, okay, so we can verify that circuit by using test bench. We can verify the circuit by using what test bench, okay. But up to FSM we can write the FSM means RTL, we can verify the circuit. But large systems like SoC design, okay, suppose if you consider Intel i7 processor or large IPs are there, okay, and Ryzen 7 processor, okay, those are nothing but SoC, system on chip verification by Verilog, it's difficult, okay. You need to go to for what RTL verification. RTL verification means you are using SV, SystemVerilog, and UVM. SystemVerilog is nothing but 90% we are using for verification. This is used for 30% we are using for design purpose only, okay. So more features will come in SV, like randomization, modularity, okay, and some OOPS concept will come. OOPS, object oriented programming concept will come. You have child class, parent class, child class, and you need to work more on functions, okay. So they will verify each and every corners of the case, that is SV, okay. UVM is not a language, this is a methodology. Okay. So you are using SV in play, so SV for the UVM and your universal verification methodologies, okay. This is UVM, okay. So that is RTL verification. You have RTL engineers here, okay, RTL designers or RTL engineers. Here you have design verification engineers, DV engineers, okay. If design is met, it will go to the next state. If design is not met, again it will go to the RTL design, okay. So if design is met, where it will go? Logic synthesis it will go. Logic synthesis is nothing but what? Some constraints will be there. What are the constraints? When you want to make an IC, you need to take care of what? Area constraints and power constraints and timing related constraints, okay. So synthesis people, like this HDL. So what is the difference between the high level language like C, C++, Java means this HDL will convert our program, whatever the program, into hardware. What is the hardware? Gate level netlist, okay, gate level netlist. So that means this is nothing but we call as synthesis. We call as what? Synthesis, okay. Converting whatever the program into gate level netlist, that is nothing but synthesis, okay. And next DFT means design for testability. This is for testing the circuit whether it is meeting the design our specifications or not, or meeting the per operation or not, they are checking, okay. Some testing techniques are there, BIST, scan test, some by using some testing they will use this DFT, okay. And next they will use LES, okay. Next pre-layout static time. There are two static timing analysis are available: pre-layout static timing analysis and post-layout static timing analysis, okay. Static timing analysis is nothing but you are dealing with the timing delays. So that means most of the ICs are operating at which one? Nanoseconds, okay. There are some setup time and hold time, related are there. Okay, that how the data is transmitting in the from input to how at what time it will be transmitting, what is the shortest path, like that. That is static timing analysis. And uh, and next, if design is met not met, it will go to logic synthesis. If design is met, again it will go to the PD flow. So PD flow, you are the PD engineers, you will study about like floor planning, placement, routing, clock tree synthesis, okay, packaging, testing, verification. Okay, so that you will study in the PD. Okay, parasitic extraction means capacitors and inductors extraction, that is parasitic extraction. And here also you have post layout static timing analysis is there. And if design is met, it will go to the next state. Design is not met, again it will go to the PD flow. Okay, so PD people will do these operations. And next, physical verification means they will do whether this operation is matching or not. We are whatever this operation you want, your design, that is matching or not. So verification is done in front end. So basically up to here, this is what front end. Okay, front end, VLSI front end, and from here VLSI back end. Okay, so after verification they will verify with some tools. After verification, what happens, so they will produce GDS2 file. So GDS2 file will be given to fabrication. So fabrication people will take these inputs and they will make the IC. Okay, so this is about so basically if you see in the VLSI, first you have RTL engineers for designing, and next you have DV engineers for verification, and you have synthesis engineers for this one, and next you have DFT engineers, and next you have PD engineers. Okay, STA engineers, and next you have PD engineers. Okay, in STA also two types of engineers, pre-layout engineers are there, post-layout engineers are there. Okay, and next physical verification engineers are there. So these many, so that means till this one we call as front end engineers, and till this one you have back end engineers. So this is about ASIC flow. Do you understood?
Yes.
Okay. Next use. So if I tell this one, you can't understand. That's why I told you. Okay. Domains: behavioral domain, structural domain, and physical domain. So see here, this is Y chart. Okay. If you understand Y chart, then you can understand this VLSI flow. Okay. VLSI design flow. First, Y chart. First, from where we will start. Behavioral domain. Okay, first I am starting for what? It is divided into three parts. Those are behavioral domain, and structural domain, and physical domain. So behavioral domain means what? First you will write an algorithm or a program or algorithm. Okay, algorithm, again it is coming to what? System. After that system, what it will come? Chip floor plan. Okay, chip floor plan. This is physical domain. Whoever the physical design engineers are there, they will do switch floor plan. Okay, after switch floor plan, finite state machine, FSM. We already seen, no? FSM, finite state machine. Okay, after finite state machine, structural domain, registers. Okay, shift registers. Okay, and next in the physical domain, what you will get? Modules placement. Where the module should be placed. Okay, that placements will come in the modules. Okay, modules. And next, in the behavioral domain, module description. Means what? How the module is operating, the description will come. Okay, and next, after module description, basically in module description we are using combinational and sequential circuits. Okay, and after that, logic gates, AND gate, that we have seen now, OR gate, universal gates like
Yes.
NAND gate, NOR gate. Okay, and special gates like XOR, XNOR.
So,
Okay, yes. And next, cell placement. You need to have the cell placement. This is physical domain. And next, again, Boolean equation. Boolean equation. Boolean equation, again it is Boolean equation made with what? Transistors. In the structural domain, transistors. And in the physical domain, you have mask. This is the Y chart. Okay, this is the Y chart. You need to remember this Y chart. Okay, so Y chart in VLSI domain. So basically, physical domain, you have this floor plan, module placement, cell placement, and mask. Okay, and next in the behavioral domain, algorithm, finite state machine, module description, and Boolean equation. And in structural domain, you have system, registers, logic gates, and transistors. Okay, so this is about this one. And the importance of CAD tools. Why we need CAD tools means, if there are 100 transistors means manually we can do this layout and design, but you have like millions of transistors are available. Okay, so we can't do. So with the CAD tools only we can do computer aided design. CAD tools are nothing but what? Computer aided design. Okay, so computer aided design. Okay, basically we are using synopsis and cadence tools, metagraphic tools, okay, Xilinx tools. Okay, so we are using so many tools in the front end as well as back end. Okay, so basic CAD tools. So these are the, as per Moore's law, I told you, complexity increases over the year. Okay, so for this designing 100 transistors manually it's possible, but millions of transistors it's not possible. Okay, so this is about process fabrication, that I will tell you in the fab. Okay. Mm, Basically physical design, physical verification, behavioral verification. Yeah, this is about comparison of 1 second. Okay, this one and this one I will tell you. Okay, comparison of FPGA and CPLDs. See here, what is the full form? Field programmable gate array, complex programmable gate array. Architecture, if you see, based on lookup table, based on the logic function. How many architecture blocks are there? Around 1 lakh blocks are there. Few blocks are available. Okay, so this architecture tuning is fine grained device, and this is coarse grained device. Okay, I told you, no, architecture memory FPGA is there. FPGA is the FPGA SRAM is there. Okay, so when power is off, all the program will be erased. Okay, in CPLDs EEPROM will be there, so this will be retained. Okay, when the power is, even though power is off, this will be retained. Okay, complexity high and complexity is less, cost wise high and cost wise less. Okay, time to on, it will take time to load the program. There will be some program in this, it will take time. Instantly it will get on. Okay, volatility, once the program is so this is once lost, once the program is off, program stays in CPLD. Why? Because this, due to this reason. Okay, and power consumption, ideal power consumption, weak power consumption, and complex to determine and easier to determine. Okay, this is about the comparison between FPGA and CPLD. Okay, basically it consists of like CLBs. These are nothing but configurable blocks. Okay, basically we are using lookup tables and flip flop, and this is nothing but mux. This is nothing but what we call a CLB. Okay, so you have lookup table, and this reset and clock will be given to flip flop, and these output and these output is given to mux. At a time, mux, I told you, at a time any input is connected based on the selection line. Okay, yes, so this is about FPGA and CPLD. And see, this one is a FPGA, CPLD, PLC, microprocessor, microcontroller, and DSP. So so full form, so programmable logic controls, these are programmable logic controls. Microprocessor, microcontroller, digital signal processor. So architecture wise, this is lookup table, logic blocks, and PLC consists of CPU, IO ports, and memory, and CPU, IO ports, microprocessor, and microcontroller, mostly von Neumann, and this is Harvard architecture. Okay, application we are using in real time application, and this is the course application. This PLCs we are using in industry application, wherever high power or high temperature is required. We have PLC controllers. Okay, computer application, consumer electronics, basically like cameras, automobiles, we are using this microcontrollers. Okay, real time applications, wherever the voice and image related processing is required, we are using DSPs. Okay, response time is faster in FPGA, slower in CPLD, slower in PLC, optimized for speed only, slow and faster for real time application. Immune to noise, so very good, moderate, high, need additional setup, low. Okay, additional setup means you need some more fans in this. Okay, good. Okay, task not designed for multitasking, single task multitasking. Okay, microprocessor means just you remember this laptops and desktops. Okay, these are used
Yes.
in multi microprocessor, not designed for multitasking. This is used for single tasking only, and this is also not designed for multitasking. Turn on time, it will take time to get on. Why? Because whatever the program is there, that should load. Less time it will take it will time to get on, and less time like that. Cost expensive, more circuitry is required. You want lookup tables and flip flops and mux. Okay, those are nothing but CLBs, configurable logic blocks. Okay, this is cheap, expensive, cheap and expensive. Okay, so this is about today's session.